Last episode, we pushed Brownian motion to its breaking point and found something impossible. The sum of squared increments, each one vanishingly small, does not go to zero. It converges to t, the elapsed time itself. This extraordinary fact comes at a price. Classical integration requires paths of bounded variation, but Brownian paths have infinite variation on every interval. So what could this symbol, the integral of w, with respect to itself, even mean? For a smooth path, calculus gives a clean answer, x squared over 2. For Brownian motion, the answer is haunted. A ghost term, negative t over 2, appears from nowhere and refuses to leave. This single extra term is the soul of stochastic analysis. It is why Black-Scholes has a second derivative term. It is why modern finance works. And it is why today the same math that Kiyosi Itô wrote down in 1944 also draws pictures through diffusion models. Welcome to stochastic integration. Stochastic. Classical calculus has a beautiful tool for weighted integrals, the Riemann-Stieltjes integral, the integral of f dg, defined as a limit of sums. F at a sample point times the increment of g summed across a partition. But this integral is only well-defined for every continuous f when the driving function g has a property called bounded variation. Bounded variation means the total up and down motion of g is finite, the supremum over all partitions of the sum of absolute increments. For any smooth curve, that sum converges to a single finite number. Now here is the key lemma. Suppose g is continuous and has bounded variation. Then the sum of squared increments is bounded by the maximum increment times the total variation. As the mesh shrinks, continuity forces the maximum increment to 0. The total variation is a constant. So the quadratic variation, the very thing that equaled t for Brownian motion, must itself vanish for any continuous function of bounded variation. But episode 7 proved, for Brownian motion, the quadratic variation is t not 0. T. This is the contradiction. If w had bounded variation, its quadratic variation would be 0. But it equals t. Therefore, with probability 1, the total variation of a Brownian path is infinite. Riemann-Stieltjes integration is mathematically forbidden against Brownian motion. So we build a new integral, piece by piece, starting from a staircase. A staircase, the simplest possible process. A simple process, or elementary process, is constant on each piece of some partition of time. Call the pieces phi 0, phi 1, up to phi n minus 1, and the partition points t0 through tn. In symbols, the process phi at time t equals phi I whenever t lies in the half-open interval from ti to ti plus 1. Finitely many pieces, finite values, nothing exotic. Now the beautiful part. For a simple process, the Itô integral is just a finite sum. Integral of phi dw equals the sum of phi I times the increment of w over the ith interval. No limit, no infinity, just multiplication and addition. With our path from seed 42, it evaluates to 0.19. But there is one absolute rule. The sample point for phi on each interval is the left endpoint. Not the middle, not the right, the left. The value phi must be decided using only information available at time ti, before the next increment of w arrives. This property is called adaptedness, non-anticipating, no peeking at the future. And here is the financial picture. If phi I is the number of shares you hold during the ith interval, then each term, phi times delta wy, is your profit or loss for that period. The Itô integral is the total gain of a trading strategy that rebalances on a discrete schedule. But real strategies are not staircases. How do we extend this from step functions to any well-behaved process? That is the second step of Itô's construction. Here is Itô's three-step strategy. Step 1. Define the integral on simple processes. That is what we just did in section 3. A finite sum, no limit. Step 2. Extend to a much larger class, called h². These are all adapted processes, whose mean squared integral is finite. Most strategies a trader would actually use live here. Step 3. Extend further by a technical trick called localization to a space called p². We will handle that briefly at the end. Let's focus on step 2. Given any process phi in h², we can approximate it by a sequence of staircases. Call them phi n. Watch the process phi of t equals w of t being approximated. 4 steps. The integral is minus 0.77, 16, minus 0.564, still minus 0.5, 1000, minus 0.47. The staircases converge to W. The integrals converge to minus 0.477. Why does this work? Two reasons. First, density. Simple processes are dense in h squared. Any phi in h squared can be approached as closely as you like by a staircase. Second, isometry. The map I that sends phi to its integral preserves lengths. The expected square of the integral equals the expected integral of phi squared. This is the Itô isometry, and it is the key to the entire construction. L squared is complete. Any Cauchy sequence converges. So the integrals I of phi n, being Cauchy because the phi n's are, have a unique limit. That limit is the Itô integral of phi. One definition, one space, one limit. Step 3 extends this to an even wider class using stopping times. But the engine of the whole construction is the isometry. Let's look at it directly. Here it is. The expected square of the Itô integral equals the expected integral of phi squared. One line, the heart of stochastic calculus. Think of a rotation. It sends a vector to a new vector with the same length. The Itô integral is the same kind of map between two infinite-dimensional spaces. Let's prove it on a simple process. Write I of phi as the sum of phi I times delta wi, square it. Two kinds of terms appear. Diagonal, where I equals j, off-diagonal, where I is less than j. Every off-diagonal term vanishes. Why? Because delta wj is independent of the information at time tj, and its conditional mean is 0. So the whole expectation collapses to 0. What remains is the diagonal, phi I squared times delta wi squared. Expected value, phi I squared times delta ti. Sum over I. That is the expected integral of phi squared. Let's check. Take a specific phi, 1, 2, minus 0.5, 1.5 over 4 quarters. Theory, expected I squared equals 1.875. Monte Carlo, 50,000 paths, 1.879. A match to 3 decimals. 3 consequences follow. 1. Because the map preserves lengths, the extension to h squared is unique. 2. The integral is a martingale in time. 3. Its quadratic variation equals the integral of phi squared dt. That last identity is the seed of something wild, the rule dw squared equals dt, which we meet in 2 sections. Now let's actually compute one, the canonical example. Now for the canonical example, the integral of w against itself. This single line is where stochastic calculus discovers it is not classical calculus in disguise. Take the left endpoint Riemann sum, w at time ti, times the increment of w over that interval, as signed rectangles under the path, green where the product is positive, red where it is negative. We want the limit of this sum. Here's the key trick, a classical algebraic identity, exact for any 2 numbers. A times the quantity b minus a equals 1/2, b squared minus a squared, minus the quantity b minus a squared. No randomness, just algebra. Apply it to a equals w at ti, and b equals w at ti plus 1. Now sum over all the pieces. 2 things happen. The b squared minus a squared terms telescope. All the interior terms cancel, leaving only w at t squared. What remains is the sum of delta w squared, which in episode 7 we proved converges to t plug in our hero path. Classical calculus says to stop at 1/2 w at t squared, about plus 0.42. But Itô says subtract t over 2, half, and that is the ghost. The answer is not plus 0.4. It is minus 0.08. The ghost term is bigger than the classical answer. It flips the sign. The integral has gone negative, where classical calculus said it would be positive. One correction, one sign flip. The entire edifice of stochastic calculus in one line. Look at what just happened. For any smooth path, one with bounded variation, the integral of x dx is exactly x at t squared over 2. No correction. For Brownian motion, whose quadratic variation is t, not 0, the same integral acquires an extra negative t over 2. That missing quantity is exactly the quadratic variation. Classical calculus ignores it, because for smooth functions, it is 0. Stochastic calculus cannot ignore it, because it is t. There is one shorthand for everything we just derived. 3 symbols, dw squared equals dt. Where does the ghost come from? One path, same seed 42. Above, the path itself. Below, for each small interval of time, the sum of delta w squared, the local squared fluctuation, 50 bars, and the diagonal, the line y equals t. Now watch the cumulative quadratic variation grow. The running sum of delta w squared up to time t. It tracks the diagonal almost perfectly. At t equals 1, it reaches 0.98. Not random, a deterministic number. 3 different paths, seed 42, seed 123, seed 160. Totally different shapes, totally different endpoints, but watch their quadratic variations. 0.98, 1.01, 1.00. 3 random paths, 1 deterministic answer. That answer is t. There is one shorthand for everything we just saw. dw squared equals dt, paired with 2 companions. dw times dt equals 0, and dt squared equals 0. The Itô multiplication rule. In classical calculus, all products of infinitesimals vanish. Itô discovered that one of them survives and equals the cleanest possible quantity, dt itself. But the rule only holds if we evaluate at the left endpoint. That was Itô's choice. What if we evaluated at the midpoint instead? The rule breaks. We get a different integral, a different answer. And seeing y is seeing Stratonovich, something else. The left endpoint was Itô's choice. What if we chose the midpoint instead? Same path. Seed 42, the one we have been following all episode. Left panel, Itô. Sample at the left endpoint of each interval. Right panel, Stratonovich. Sample at the midpoint. Let's compute both sums at the same time on the same path. Watch the running totals. Itô converges to minus 0.07. Stratonovich converges to plus 0.42. Same path, different sample point, different answer. And the difference? Plus 0.49, almost exactly 1/2 of t. In fact, there is an exact conversion. The Stratonovich integral of w equals the Itô integral of w plus t over 2. The ghost moves from a mysterious correction to Itô to an extra term in the conversion formula. There is a beautiful consequence. Stratonovich recovers the classical answer, 1/2 w at t squared. The midpoint evaluation magically cancels the Itô correction. Symmetry undoes the ghost. So why does finance use Itô? 3 reasons. First, adaptedness. A trader can only act on information available now. The left endpoint respects that. Second, the Itô integral is a martingale. 0 expected profit from a hedge is exactly what we want. Third, the Itô isometry. Variance is clean, easy to compute, easy to bound. Stratonovich is what physics and geometry choose. Itô is what finance chooses. And now, one final world where Itô's integral lives. The Itô integral, born in 1944 in Japan for decades, a tool of mathematical finance. But in 2020, it appeared somewhere new. The reverse-time stochastic differential equation that powers every modern image generator. And the last term, g times dw bar, is the same Itô integral. Here is how it works. Start with an image, a pixel art face. At each time step, add a bit of Gaussian noise. This is forward diffusion. As time progresses, the image melts into pure noise. To reverse it, we integrate the reverse SDE one small step at a time. Using Euler-Maruyama, each step is the current image minus a score-based drift plus g times the square root of delta t times a standard Gaussian z. But g times square root of delta t times z has exactly the distribution of g times delta w, an Itô increment. Every reverse sampling step is a finite Itô integral step. 3 papers, Anderson 1982, Ho Jae Nabil 2020, Song et al. 2021. Itô's object from 1944 now paints images in 2026. One final piece remains. How do we differentiate with these integrals? The chain rule that ties it all together. In 20 minutes, we built the Itô integral, from why classical calculus fails to the finite sum definition on simple processes, to the L-squared extension, to the isometry, to the canonical example, to the calculus rule, dw squared equals dt, to the comparison with Stratonovich to its role in modern image generation. But one piece is missing, a chain rule. How do we differentiate a function of w? Start with classical Taylor. The differential of f of w is approximately f prime of w times dw plus 1/2 f double prime times dw squared. Substitute the Itô rule, dw squared equals dt. The result is Itô's lemma. The differential of f of w equals f prime times dw plus an extra half cf double prime dt. This extra term is the fingerprint of stochastic calculus. Look what happens when we pick f of w equals half w squared. F prime is w, f double prime is 1. The differential becomes w dw plus dt over 2. Integrate from 0 to t and you get back the section 6 result in one line. The ghost came from here. Itô's lemma manufactures it automatically. That is episode 9. The chain rule that ties it all together. See you next time.